Hello viewers, my name is Damilare. In this lesson, we'll be looking at the topic transition metals. The first word there is the word transition. When you hear transition, the literal meaning of transition is that something that is moving from one place to another. For example, if you consider periodic table, this is just the sketch of a periodic table. You notice that there are some elements here on the left, that's group 1, group 2. You also notice that there are some elements on this side. But before you can move from this left to this right, so you have to jump this middle. So this middle where you are jumping shows that is a transition. Like when one dies, they will say transition to glory. So meaning that those elements that are in between those ones on the left and right, they are the transition elements, and they are majorly metals. So these elements, they are said to be incomplete in terms of their filling of electrons. So the filling of electrons is incomplete. So they call them partially filled electrons or incomplete inner shells of the electron. Why do they call them incomplete? The reason is because when you look at, according to Hofbauer principle, in the arrangement of electron, we have this kind of drawing, 1s, 2s, and so on. When you are taking your configuration, you take it as 1s, 2s, 2p, 3s, 3p, 4s, then you come to 3d, 4p. Now this 3d, that's where the transition is, and 3d, the highest of d is 10. But any elements that you found before that 3d 10, they are the transition metals. So meaning, for example, look at argon 18. I've arranged them here, 1s2, 2s2 down to 3p6. If I want to look at potassium, I will include 4s1, calcium 4s2. But transition metals now, if I start from scandium, I will say 3d1, titanium 3d2, vanadium 3d3, chromium 3d4, manganese 3d5, iron 3d6, cobalt 3d7, nickel 3d8, copper 3d9. Meaning that by the time I reach zinc, instead of 3d10, though the 3d10 will surely be written, but this zinc is not usually considered as transition metals because of that 3d10, which has been filled already. But those ones that are partially filled, that are not up to that 3d10, they are the ones they majorly focus on as the transition metals. So meaning that if we say they are incomplete inner shell of the electron, so it means they are referring to those ones that are before the 10th one. So that's some of the points we have under transition metals. Now, where is their location? According to that structure I put here, look at this drawing here. So it means if you check your periodic table, you will see group 1 and group 2 here before you see this space. So mean that after group 2, if you should jump to this place, this is group 3, 4, 5, 6, 7, and group 0. So between that group 2 and group 3, that's where you see transition metals. That's if we want to consider the periodic table as from group 1 to group 8. That's when we say the transition metals are between group 2 and 3. But if we want to consider the periodic table as from group 1 to group 18, it means we will say it is found in group 3 to group 12. Meaning that you say group 1, group 2, then here you start saying 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then the one that ought to be group 3 will now be your group 13. So meaning that we call it group 3 to group 13 if you want to consider 18 groups. So that's the location of the transition metals. Now, how many transition elements do we have? The total number, if we want to consider only the D block, we say we have 40 of these transition metals. So they are found here in this region from here to here. So they are 40. Why? Because if you check your periods, so you say after this period 4, this is a period 4 here, period 5, period 6, period 7. So that means from period 4, 5, 6, 7, that's 4 rows. So these 4 rows make up 40. And looking at the group, there are 10 groups here. So 10 groups, 4 period, that's 40. Now that's for the D block. But we now have those ones that are called the lanthanides and the actinides. This one also can still be considered as transition metals, but we call them inner transition metals. They are actually 28 because they are the F block. F has 14, so meaning that 14 for the first layer, 14 second, that's 28. So meaning that we have said 40 from the D block, but from the F block we say 28, that's 14 14, so total will be 68. So meaning that we have 68 all together for all the transition metals, 40 from the D, then 28 from the F block. But take note that this 68 is not fixed, because we can begin to remove some of these metals because they may not be obeying the definition of transition metals. From the definition of transition metals, they said those ones that are not completely filled. So if we want to look at those ones that are not completely filled, we begin to remove some of them. For example, we have to remove zinc. Zinc will not be considered as part of transition metals. Why? Because zinc is completely filled. If you look at zinc, the last one is 3D10, so and 10 is already filled. The cadmium, that's CD. Cadmium also will not be considered as transition metal if you want to look at the definition. The same thing, mercury. So and that's why that total number of 68 may not be fixed. So that is for the total number of transition metals. Now let's now consider the those shells. Each shell we encounter while drawing our configuration. That why is it that after 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s1, 4s2, then why going back to 3d? That means numerically it's supposed to be increasing. That after 4s1, 4s2, that how come is 3d1 in this position? So the reason why it's having this 3d1 as the next one is because the 3d1 is actually higher in terms of energy compared to the 4s2. So 4s2 has a lower energy while 3d1 has higher energy. That means we are not considering the numerical form, because numerically 3 ought to come before 4, but in terms of energy we'll pick 4s2 as a lower energy, then 3d1 has higher energy. So that tells us that 3d is greater than 4s. But when you compare it with p, like 4p, so 3d will now be lower than 4p. So the summary of all this, you can just check this off-bow principle, the drawing, that 3d comes before 4p, meaning that 3d is lower than 4p. But in terms of 4s and 3d, so 3d is higher than 4s because you would have taken your 4s before taking your 3d. So that's in terms of the arrangement of the electronic configuration. Now there are some switching that can take place while writing your electronic configuration. For example, especially those ones that are always close to 5. That means those ones that are close to 5, like 24 is close to 25, 29 is close to 30. So those elements that are close to them, like chromium and copper, we can switch the arrangements of the configuration. For example, look at chromium 24. You know, when you are writing 1s2, 2s2, 2 pieces, 3s2, according to this arrangement, 3s2, 3 pieces, 4s2, the next one ought to be 3d4, 3d4. But this 3d4 will not be written. Why? Because there is a kind of instability. So chromium, their energy is unstable. So because they are unstable, the 3d4, it will rather take 1 out of the 4s2 and give the 1 to the 3d4 to make it 3d5. Now the 3d5 will now come here, while out of the 4s2 it will change back to 4s1. That's for chromium. The same thing for copper 29. Copper 29 ought to be 1s2, 2s2, 2 pieces, 3s2, 3 pieces, 4s2, then 3d9. But we won't write the 3d9 because it is unstable. That means, why is it unstable? That 3d9 is showing that it's very close to 10. So it has to take 1 out of the 4s2 and then become 3d10, so that the 4s2 will become 4s1. So take note of this arrangement. Now we move to the physical properties of transition metals. Transition metals, they have high melting point. You know, they are metals, so high melting point and boiling point, they are very hard. So they are hard since they are metals. So they are hard, they are dense, like heavier, that they can easily sink in water. They are lustrous, meaning they can shine when you paint them. They are stronger, harder than S block. Remember that S block elements, they are also metals. That's all those group 1 and group 2, talking about sodium, potassium, they are metals. But the metal of transition metals, they are stronger and harder than them. They are good conductor of heat and electricity since they are metals. Another thing is the reason why their melting point and boiling point is high is due to the number of electrons they have per atom. There is a lot of electrons in them. So that's from the 4s and 3d. So they can easily bond with so many other elements. So their atomic number also is very large. They have large atomic number, more electrons, so which will cause reduction. So they can easily reduce size of other substances in comparison to S block. Now, the chemical properties of transition metals. What are the chemical properties? So all those transition metals, they have similar chemical properties since they are all incomplete orbitals, like they are incompletely filled d orbitals, or you say partially filled d orbitals. So looking at their chemical properties, number one, they have variable oxidation states. Variable oxidation states, that means their oxidation states varies. For example, when you look at manganese, manganese is a transition metal and it is in number 25. So this manganese, you can see various oxidation states. That's why you can see it as MnO2. I mean MnO, just MnO, that's manganese 2 oxide, manganese 2 oxide. This same manganese, you can still see it as manganese 4 oxide, MnO2. So meaning that it has +2 in manganese 2 oxide and it has +4 in manganese 4 oxide. So talking about variable oxidation states. Apart from that, you can still see it as tetraoxomanganate. Tetraoxomanganate ion, so that's MnO4 2 minus. If you look at oxygen, the oxidation number of oxygen is -2 times 4 is -8. By the time it crosses to the other side, so it will become +8. And this -2 here, whenever you are trying to calculate oxidation number, it will arrive at +6. So meaning that tetraoxomanganate, it appears as 6 here. So +6. In another form again, it appears as +7. That's from this way is tetraoxomanganate 7 ion, but this one tetraoxomanganate 6 ion. So I can see the variable oxidation state as +2, +4, +6, +7. So that's variable oxidation state. And each of these oxides of the transition metal, like the manganese, so it can form a basic oxide. A basic oxide can also be ionic, that means positive and negative. It can also act as reducing agent, so ionic, reducing agent, and as a basic oxide. So they also have higher oxidation states, like you can see it in KMnO4, that's tetraoxomanganate, and in chromium. Chromium is another transition metal having higher oxidation states. So potassium dichromate 6. So here now it can act as covalent and as an oxidizing agent. So meaning that the same transition metal that is acting as a basic oxide, ionic, and reducing agent here, so can also act as a covalent oxidizing agent in terms of their states. So there are some that they have intermediate oxidation. Intermediate, that means just middle. Intermediate oxidation, so like MnO2. So that's for it. Now let's move to another chemical property of transition metals. They can form complex ion. They can form complex ion. How? That's showing a ligand. A ligand is just like a large combination of elements, so they can form ligand. For example, look at this ion, we call it hexaquarium 3 ion. The hexa is this 6, the aqua is this water, then the ion, so this is the ion. So hexaquarium 3 ion, so this is the 3 ion, this is the aqua, then this is the ion. So hexaquarium 3 ion. So this is a complex compound formed using the transition metal ion. Also, that same transition metal ion can be used for hexacyanoferrate 3 ion. So whereby we use our ion as a transition metal and the ligand is there. Cyano is the ligand, just like aqua here is the ligand. Also, if you look at copper tetraimine, that's another complex substance formed using copper, which is one of the transition metal, where the ammonia represents the ligand. So this is copper tetraimine, another complex compound. So let's look at another chemical property of transition metal. It can form colored ions. So they are majorly colored. So they have different colors, except zinc. And that's why we said there are some exceptions. There are some of those transition metals that are not fully transition metals based on this property. So because looking at zinc and scandium, they appear colorless. So since they appear colorless, so they may not be fully taken as transition metals. So now there are different kinds of colors. Each of them will be given us. For example, if you look at, we have said scandium is colorless, and take note of the oxidation number of scandium is 3+. So you can say scattering. Use it to remember the 3. Scattering, it means scandium. Then, and we say it is colorless. So then the next one is titanium. For titanium, that one is 3+. So titanium is, you can use the letter T and the 3. Titanium 3. So then, or you say trinity. Titanium trinity, just like scattering trinity. So this one here, the titanium, it is purple. You can use tip to remember, letter P. Titanium is purple. So talking about the different colored ions they form. Then vanadium, that's V3. You can say like victory. So vanadium is 3+, and the color is green. You can use very good to remember, V and G. Very good, so it's green. Then chromium is 3+. You can say crotria, just like the country, crotria or country, 3+. So this one is violet color. Violet, so you can say CV, like curriculum vitae, so violet color. So showing the different colors of the transition metals. Then we have Mn, manganese. So you can say mount tree, maybe someone that is mounting the tree, mount tree. So the color is violet, so you can use move, or just use move, M and V. Manganese is a violet color. So, and we have it in different form. We have the 3+, then we still have another ion here, that should be 2+. So after manganese, we also have iron. We have iron 3+, we also have iron 2+. So for the iron 2+, that one is green. So this is the iron 2+. So it is green in color. So it can appear as green. So that you can use FG, like federal government, to remember the color, which is green. Then the iron 3, that one you can call it yellow, you can call it brown. So iron 3 is brown or yellow. So if you put brown, you can say February, F-E and B, February. Why this one is federal government. So that's iron. Then cobalt, you can say copy, like copy. When you copy something, that's pink. They are pink in color. So, and the oxidation number is +2+, just like carbon 4 that has CO2. So use it to remember that it has 2 ion, cobalt. So it's pink. Then nickel is the next one, Ni. You can use Nigeria to remember, G, which is green. So nickel is green. So that's for the nickel. So it's also 3+. So 3+ for the nickel. Then we also have copper. So copper 2 ion. So for copper 2 ion, that's 3D. So that's 2+. So the color is blue. You can use cob, just like lion's cub, CU and B, cob. So copper is blue and it's 2 ion. Then we have talked about zinc, that it is colorless, but the oxidation number is actually 2+. So here we have seen that the chemical properties of these transition metals, that they appeared in form of colored ions. So colored ions. Then the last one is catalytic properties. So meaning that the transition metals can appear as catalysts. For example, look at the manganese here appearing as catalyst. Manganese, that's manganese 4 oxide. So that's when you are trying to do your water formation, or splitting of water. So we use manganese 4 oxide as your catalyst. That's when you are splitting your hydrogen peroxide into water and oxygen. Then in the formation of ammonia, we can also use iron as our catalyst. That's when nitrogen and hydrogen come together to give us ammonia. So we use iron as our catalyst. Also in the production of H2SO4, if you want to form your sulfur 6 oxide, so sulfur 4 oxide and oxygen, you use vanadium 5 oxide as your catalyst. Then also in organic chemistry, while doing formation of ethane, so taking your ethane and hydrogen, you use your nickel as your catalyst. So you can see all those transition metals appearing as catalysts. So thanks for listening.